Right. Let's get started. So I'm very happy today to introduce Brian Swingle as our seminar speaker. Brian did his undergraduate degree at his PhD at MIT in 2011. And then he went on to do postdocs at Harvard and at Stanford, supported during that time by a Simons Fellowship and the from Qubit collaboration. In 2017, he joined the faculty at the University of Maryland and was there until 2022 when he became a professor at Brandeis, where he currently is. And Brian's research explores a wide set of connections between quantum information theory, quantum many-quantum physics, quantum field theories, and gravity. I think Brian is actually quite unique in his ability to translate between the languages of these fields and even to translate sort of fundamental questions onto capabilities of current or near-term quantum science experiment. His pioneering work has included connections between tensor networks and quantum gravity. So you study the relationships between quantum chaos, information scrambling, and black holes, and devised experimental probes of quantum information scrambling, so inspired ideas that have been realized in experiments. And furthermore, touched on connections of quantum error correction and actually near-term ideas for near-term algorithms in hardware. So I think you can see Brian is very broad, and today we're going to enjoy hearing about looking inside black holes with quantum methods.
Great, thanks a lot, Monica. Nice to see you all. Thanks for having me. It's nice to be back. And yeah, today I'm going to tell you about looking inside black holes and the quantum science connection because it's going to be sort of a strong notion of quantum randomness looking inside for us. So the kind of context for this work is the theoretical problem of quantum gravity. So we're trying to put quantum physics and gravity together. And when I talk about black holes, I'm going to not be talking about astrophysical black holes. Unfortunately, we'd love to do that, but we're not there yet. And so we're going to, think about black holes in sort of a toy universe and try to understand how to make sense of what's going on with black holes. It turns out black holes are sort of a cornerstone problem in this field. And once you understand that, you understand a lot. And why is looking inside interesting? Probably the one thing I know about black holes is that you can't see out once you're inside. So somehow it's very hard to know what's going on inside the black hole. And this sort of intuitive feeling is actually borne out in the precise theory. It's very hard to sort of figure out what's going on inside, to understand what it means, sort of microscopically, quantum mechanically. And so when we have a quantitative, precise tool to look inside, which is what I'll tell you about today, it's sort of interesting. So that's the kind of broad context. This picture here is a picture that I made with the help of Midjourney, which is one of these image generators. This is how I spend most of my time, honestly, these days. You can see Midjourney is the first author of this picture. So it's like a grad student. It does all the work. I tell it what I think is good or bad, and I pay some money. So in that sense, it's very similar. This is a spotted wormhole, which you'll see, hopefully, the connection to the talk later on. And yeah, let's get started. Please ask questions at any point. So I want to start with kind of a preview. We're going to look inside black holes a bit and find what I'll call Einstein-Rosen caterpillars. This is a play on the idea of the Einstein-Rosen bridge, which is supposed to be a wormhole that connects two different black holes together. So the way to think about this picture is that there's a left and a right. And if you're out here looking in, this looks like a black hole horizon. If you're over here looking in, this looks like a black hole horizon. If you look inside, there's some structure. There's some spatial structure inside this geometry. It looks like a long tube, but with little segments in it where there's, in this case, this matter, some dust or something. And this sort of featureful wormhole here is going to be our caterpillar. So it looks a little bit like a caterpillar with little segments. And we're going to understand something about how to translate the properties of this caterpillar into something you can see from the outside. That's the idea. More microscopically, this is kind of what the caterpillar is going to look like. It's going to look like our wormhole with the left and right black holes, we're going to have lots of spots and features to it. And these spots or features are going to be very analogous to what in quantum information we think about as random circuits. So we have a bunch of qubits, there's a bunch of gates, or 2 qubit unitaries that act between these different qubits. And I could say choose these different unitaries randomly, for example, that would form a kind of random circuit architecture. And as time progresses, as you make this circuit deeper and deeper, you get sort of a more and more random state or more random unitary. And that's a useful thing for lots of purposes. And we're going to have a strong analogy here, whereas the wormhole gets longer and longer, it becomes more and more random in a certain precise sense. And that tool let us say something about the properties of the wormhole. So that's at a high level where we're going. Here, I'll just flash a technical statement that will explain all these words later. But the basic point is that we're going to consider a whole bunch of these caterpillars, all different kind of spots. And what we're going to show is that they have some typical or average length L. And when you have a certain length of caterpillar, it's going to correspond to a certain degree of quantum randomness as indexed by this parameter K. K is K of a K design. It tells you sort of how like a Haar random object this thing is. Okay, so the larger K, the more Haar random like it is. And we're going to see that as the wormhole grows longer, it becomes more and more random. That's the essential story. And I'll just highlight that I'm going to tell you a much bigger picture story, but the precise technical work is something that we did just at the end of last year with super awesome postdoc Martin Saciada, who's headed to Berkeley next year for another postdoc, and Javier Magan, another awesome guy who's in Argentina. Okay, and this is the paper from December of last year. So that's where we're going. I'll explain what these things mean in more detail in a bit, but let me start over now and kind of set the stage. Why do we care about black holes? Why are they interesting from this point of view? So here's a black hole. This is, a sort of image or processed data from the Event Horizon Telescope of the supermassive black hole at the center of our galaxy. The interesting thing that we learned from Beckmann and Hawking is that black holes have an entropy. And this entropy is very large, actually. If you're like an information theorist, in order to have a card carrying information theorist, you have to you're obligated to study the most entropic objects, right? And these things are by far the most entropic objects in the universe. This number, if you put it in here, this is Newton's constant and Planck's constant, so it combines these two things together. This number is enormous. It's much larger than all of the entropy and all of the thermal radiation in the entire visible universe by a fair margin, okay? So these are really, from this point of view, mysterious objects. The fact that the entropy is proportional to the area is also mysterious. If you think about thermodynamics, normally the entropy is proportional to the volume, to the amount of stuff. So there's something really fundamentally weird going on here. And that can give you your first clue that there's something interesting, something really important about thinking about black holes. So they have a lot of states, but they also have interesting dynamics. So here is data from LIGO, from the famous merger. And you see there's these two objects that are coming together to merge. And then at the end here, there's a ring down. So that's this kind of loss of amplitude here. I've circled it there. The time scale for this loss of amplitude, this ring down, is just set by geometrical properties of the black hole, like the light crossing time. But if you have an entropy and an energy, the mass of the black hole, you can get a temperature. And if you then express that time scale and move to the temperature, you get this very interesting sort of fundamental quantum thermal time scale, which is just something set by h bar and the temperature of the system. This is the kind of time scale that people have been interested in and talked a lot about in condensed matter physics. We're trying to understand strongly interacting systems. Maybe this sort of so-called Planckian time is some sort of bound on how fast things can scatter or evolve in some sense. It's a bit vague, but this has been a very inspiring idea. And so black holes sort of have lots of states, and they have equilibration at an interesting time scale. Okay. So from the outside, they really look like what we would call chaotic quantum systems. But what about the inside? So here is metric, space-time metric of the Schwarzschild black hole, which is a black hole in flat space. You can see the really important factor here has been red. This is the factor that tells you something interesting is happening at the event horizon, which is r equals 2gm. And the picture that you should have in your mind for this is that far away from the black hole out here, you have your light cones that look just like they do in ordinary fun space. But as you get closer and closer to the horizon, the cones sort of tilt more and more until eventually they're tilting so much that you cross the horizon. And now in your future is only singularity. This is the singularity inside the black hole with r equals 0. So it's sort of not so much that there's no where to go out of the black hole, but no when. Like your future is just inevitably the singularity. So there's really like an exchange between what is space, r here, and what is time, t out here. They exchange roles inside. Space becomes like time, and time becomes like space. And so now there's like an enormous volume of what we would think of as space if you're inside here. And it's like the question you can ask is, what is the meaning of this enormous quantity of space? In particular, I told you that the black hole has finite entropy, but it looks like there's a huge amount of space inside here. So how does that reflect in this finite entropy? That's a very basic question. Where is all this space coming from? How do I think about it? So what we're going to do then is try to understand this question. What does the amount of space inside the black hole mean precisely? What does it measure? And as I said, we're going to sort of swap out astrophysics for this toy universe that I'll introduce in a moment. And this toy universe is very different from our universe, but it has still black holes. They still have entropy equal area, and they still have the fast dynamics. Okay, so they kind of preserve the properties that we're interested in, but in a much more controlled setting. So this is another mid-journey picture. This time it's on my shirt, coordinated my outfit. This one is conveying that you have some kind of shell here with little squares. These squares are qubits or rubidium atoms or something, some quantum degrees of freedom, and somehow they're going to generate from their interactions some internal space in which there are stars and gravity and this sort of stuff. So that's the essence of holography. But here's what we're going to use. It's the technical machinery that's the groundwork of the talk. It's this thing called the anti-de Sitter space conformal field theory correspondence. The abbreviation ADS-CFT, or just holographic duality. And what you should have in mind is that there's sort of like a skeleton, like the outside of a soup can. And this skeleton is a fixed, rigid skeleton. It's where the boundary degrees of freedom live. This is an ordinary quantum field theory, some ordinary quantum many-body system. It's a little bit exotic, but it obeys the usual rules of quantum mechanics. So there's no gravity. And what is supposed to be true is that this system is exactly equivalent to another system which lives inside the can. There's no interior here. It's just really the skeleton, but secretly somehow this generates the interior. The interior has dynamical geometry, it has gravity, it has planets and stars and all that stuff. And so if we want to learn about this, which is mysterious, then we can try to map it to this, which we understand much better, and thereby learn some lessons. Good. So I want to just make a point here, which is that although this is not our universe, it's still very, very interesting. You've probably heard that putting quantum mechanics and gravity together is very hard, but in this universe, they go together like, peanut butter and jelly. They really not just like they work together, but they fit together very beautifully in some essential way where geometry is intimately tied with entanglement, complexity, all the things we love in quantum science. So it's not just there's no conflict, as Professor Vader would say, but that really they're like two sides of the same thing. So even though it's not something that directly describes quantum gravity in our own universe, it's very interesting as a proof of principle and as a theoretical lab. What also excites me and how I actually came to this, I'm originating this matter theorist, but I came to this because this structure connects actually to lots of things in quantum matter. That's how I came to this story, actually. I started from the quantum matter side of it. And so those connections are very interesting. it also potentially enables you to try to realize this duality in an actual lab experiment and thereby learn about it. I'll come back to that later. But so it's very exciting already at that stage. Of course, the problem of understanding what's going on in our universe is still a big challenge. We have a cosmology, we have maybe a Big Bang, we have expansion, acceleration. Those are lots of non-trivial ingredients. There's no ADS boundary anywhere. So what's going on? I'm working on that too. That's a different talk. So if you want to invite me back, I'll happy to tell you about that instead. But that's the scenario. So let me tell you a little bit how it works. Here is one of those blue slices. This is one of Escher's nice prints. The fish are all the same size in the hyperbolic metric that you get in this anti-de Sitter space. And the distance from here to the true boundary is infinite in space, although light can reach there in finite time. So it's some sort of unusual place. This is like empty space, but with the negative curvature of hyperbolic geometry. This empty space, simplifying a little bit, is equivalent to the ground state of the boundary. Just the state where there's no excitations, that's empty space. If you want to get a thermal state, what you should do is you should heat the system up. And so you make the boundary hot, you put some temperature, that translates into bulk, again, simplifying a little bit into the presence of a black hole. So these are the two basic ingredients. And we can think about our wormholes in this context as well. Here I've shown this little red dot as like a trace in this so-called Penrose diagram over here. So this is the diagram that's distorted space and time, but it's preserved causality. So light still travels at 45 degrees. And so in this picture, you start from the boundary, you go in, you reach the event horizon, and then you can actually extend the geometry. You can keep going out to another side, or you can go kind of into the interior. And it's this interior region that we're going to try to understand. But there's the singularity again. And so from the point of view of that picture before, where I was talking about this mysterious amount of large space, that's roughly analogous to some curve or volume that goes like that inside.
Why do you say roughly analogous?
Well, yeah, it's the same thing. Yeah, I don't remember why I put that weasel word in there. I'm sure I had some reason. But yeah, so this large amount of space translates into some large amount of space inside here, and that's what we're going to understand. So here's kind of to set up the precise question. Here's our wormhole now, our Einstein-Rosen bridge, no caterpillars yet, just a bridge. At 0 time, it's a geometry which just goes to the horizon and then comes right out again on the other side, and it looks like this. This is the left boundary here, this is the right boundary, this is the horizon. You can't traverse this wormhole, because you can see if you sort of start here and go at the speed of light, you end up with a singularity, not over here. But it is a spatial bridge that connects the two sides. Now, suppose you kind of go up in time, that's up this diagram on the left or the right or both, then you can ask for some notion or measure of the wormhole, like what happens to the wormhole at this later time. And it turns out what happens to the wormhole is just gets longer. So this tube in the middle here now, this kind of flat-like part, that corresponds to this green segment that's inside the dashed lines. That's the interior. And it's that growing interior that we want to understand. That's the basic question. So that's the question of the talk. What is the equivalent? What is the dual of this growing interior? What does it mean from the point of view of the CF? So your first guess might be, okay, I know about chaotic quantum systems, correlators decay with time, yeah. So maybe it's just some decay of correlations, right? And that's not sort of wrong, especially at early time. It is related to that growth of the interior. But there is an issue. Here's a correlator that's decaying exponentially with time. The issue is that this doesn't last forever. If there's a finite entropy, which we said there is, then you expect that there's going to be a sort of minimal, maybe quasi-random value of this, which is set by the entropy. So it's very small, but not 0. And exponential decay is pretty fast, so it actually reaches that minimum value pretty quickly. And then you don't have decay anymore, you have fluctuation. So it looks like this decay is sort of, it tracks the growth for a while perhaps, but then kind of as a clock it stops working, or it becomes more complicated to occur. So these sort of simple probes don't seem to capture, at least at long time, what's going on. We want to have some other way of thinking about things. So this led to the first answer, not answer 2, but answer 1, which is that the growth of the interior is equivalent to the growth of the computational complexity preparing this state. So this is an idea that Lenny here put forward some years ago. I worked on this, Douglas worked on this, many folks here worked on this and around the world. And the idea is sort of like this. This is the thermofield double state of the CFT, which is equivalent to that wormhole that I showed you before. I didn't prove this, I'm just claiming it. If you evolve in time, that corresponds to putting this phase factor on the state. And the idea was if you just ask at a given moment in time t, how hard is it to make this state using 2-qubit gates? The answer should grow with time. It should grow with time for a long time. And you might expect that the rough growth would be the number of degrees of freedom, that's the entropy, times the clock rate that they're computing at, which is the temperature. Because that's what we said was the fundamental time scale for the black hole, where it brings down the time scale set by 1 over the temperature. So this is like the clock rate of the computer, the number of computing degrees of freedom, and so that's how the complexity grows. You're just applying that many gates, roughly speaking, per unit time. Okay. So let me explain why I think this is a sort of reasonable thing. Why should you think this is not a crazy idea? Well, let's go back to the ground state, and let's ask ourselves, how do we understand from the CFT perspective what the ground state is? So forget about black holes for a second. Let's just understand what is this emergent space, right? So here's my space again. And the idea that I proposed many years ago now is that we should think of this bulk geometry, the geometry of the gravitating region, as some sort of picture or characterization description of the entanglement of the boundary degrees of freedom. So my true physical degrees of freedom are like these open lines at the edge of this network. Those are the true qubits. There's no other sort of free degrees of freedom inside, but there is some network of tensors of some objects which connect up. And if I contract all these tensors together, I get some quantum state on the boundary. But that quantum state has a pattern of entanglement that's reflected in the geometry of this network. That was the idea. So the bulk is really a picture of the entanglement pattern of the boundary. And this idea has some teeth. For example, in ADS-CFT, the way you compute the von Neumann entropy of a boundary region is you make your boundary region in the dashed line here, and then you look for the minimal curve in the bulk, which ends at those two ends, like this. And then the area or length of that curve in Planck units is the entropy. So this is like our old black hole story again, but now sort of more general. And if you go to this network, which has the same kind of hyperbolic kind of 2-to-1, force straining structure as over here, then you find if I cut a certain number of bonds, this would give me an upper bound on the amount of entanglements that could exist between this region and the rest of the network. So there's a kind of rough matching between cutting lengths in the tensor network to estimate entanglement and the precise formula over here, the Reed-Huntington formula for computing entanglement. And it gets better, we can actually add black holes to the story. That corresponds to the network to, say, chopping off some degrees of freedom and putting like thermal states there or something like that. And now what happens to your minimal curve on the gravity side is it kind of hugs the horizon of the black hole. And over here, now you can cut bonds, but you have to cut lots of bonds along the length of the black hole. And so you again have a kind of co-elevated match. But now you have, in addition to entanglement, you have sort of thermal entropy coming from this part of the black hole horizon. So it's kind of reproducing that black hole entropy now, but in the larger context of this von Neumann entropy. Okay. And you can put it all together to make so what you might call a wormhole network. Take one of these RG-like networks for the left, one of them for the right, glue them together, maybe you have some other network in the middle, which is like more planar, right? And the idea would be that the combination of these things is what's equivalent to this state. And the outside is going to stay the same, but the interior is going to grow longer and longer, just adding more and more gate to this interior. And that is going to correspond to the growth of it. And again, there's sort of some teeth here. If you think about this network as an RG network, then what it means is that different layers correspond to different time scales or energy scales. As you move down the network, energy gets lower, so time scale gets longer as things move more slowly. So you kind of imagine force training or normalizing from the UV, where your energy scale is set by some Hamiltonian term, some microscopic term, down to this other low energy scale set by the horizon, where the time scale is set by the temperature. And so then you have how many legs here? You have entropies worth of legs. They're computing at this rate of 1 over the temperature or the temperature. And so you can sort of actually quantitatively argue using like this network does an RG transformation. You can quantitatively argue that the time scale of the Hamiltonian has effectively slowed down from that kind of the UV microscopic scale to this scale of them. And you've also decreased the degrees of freedom. And so you kind of have at least a heuristic, but a precise heuristic within this framework of this temperature times entropy complexity. Okay. So let me make it a little aside here now. That was a lot of pictures, but I want to convey that there's something a little bit more going on here. Something that's closer to like qubits and the kind of things that some of you might be interested in. So here's this cartoon I had of the network. I've grayed out a big part of it. Let's just look at a little chunk. We can try to instantiate this precisely as some microscopic structure, such as this structure that Isaac Kemenai called a deep mirror. There were D-mirror for short. So you have some like boundary here, you apply some rows of gates, then you kind of have some product states here, and only half of the degrees of freedom go through. So it's decreasing the degrees of freedom by a factor of 2 each time. That's like the decrease of degrees of freedom as you go in. And the idea is that this is a variational ansatz. I think this is a variational ansatz for the ground state of the CFT. We vary all the parameters of these gates, and maybe we can get a good approximation to the ground state of some system.
And the vertical lines.
Yeah, this is the scale direction, or the radial direction. I mean, it would be lab time if you're going to make this in an actual lab, but here we're thinking of it as scale. And this actually works quite well. There's lots of lattice models where you can use this, and it's been shown to give you very accurate solutions for the theories. And more recently, one thing we did was we generalized this to describe thermal states. So take the network for the ground state. These are sort of high energy, medium energy, low energy, but product states. Now we're going to turn them into thermal states. Or we're going to excite them a little bit by an amount that's related to how much energy they have. So these are excited only a little bit. These are excited more. These are excited still more. So we have 2 copies of the network here and here, and these thermal states now, which are exciting them. And this then we propose as an ansatz for the thermal physics rather than for the ground state. You take the ground state, you modify it in a specific way, and you get an ansatz, which we call thermal mera or T-mera for thermal state. And in principle, this is another variational ansatz. You can calculate the free energy now efficiently in this ansatz. That's a non-trivial thing, but it's true. So you could variation optimize this to get an approximation for the Gibbs state instead of the ground state. And it actually works really well. So here's an example. 512 qubits. Of course, we're doing it on our computer for a model that we can solve analytically, so we can do everything. We have 512 qubits. We're actually not doing any variational optimization of the tensors at all. We just take the ground state tensors, we add in these thermal states with a given energy distribution, which just comes from the fact that this energy is going down every time you go down a layer. So there's really only one variational parameter. On the left, you can see energy density versus entropy. The dashed line is the correct answer. And you see if you take, depth 4, 5, 6, they're all quite close to the dashed line. So we're accurately reproducing the entropy, the thermal physics of this scale invariant conformal field theory using this ansatz. On the right here is the fidelity. This is the fidelity of the entire quantum state between our ansatz and the true Gibbs state. For 512 qubits, it's around a half. So that's enormously high fidelity. That means we're like almost preparing the full many-body quantum state with 500 qubits using this simple network where we actually didn't even do any variation optimization. So the message here is that there is something powerful and non-trivial about these pictures. They can be turned into very powerful tools. Of course, this is a special example, so it's interesting to ask whether it generalizes. I think the principles are all there, but it's something that I think is worth thinking more about. Okay. So that's the end of the aside. Just wanted to put something in there for the non-gravitationalists among you. So let's just summarize this part with the question, is complexity enough? There's no doubt it's been very, very productive and inspiring to think through this. There's a million papers that have discussed this physics. But at the end of the day, complexity is just a very hard beast to put down precisely. Very hard to say the complexity of this state is precisely this. It's not even something that makes a lot of sense in field theory unless you do some work to define it properly. And so it sort of has the right spirit, but maybe we can have something else that's related, but a little bit more precise and make some progress. So that's where randomness is going to come into this. So what we're going to do now is we're going to relate the growth of the interior to the growth of randomness. That is actually related to the growth of complexity as well. You can't have very random object that's not also fairly complex. So as a byproduct, we'll sort of end up proving the complexity thing in some form anyways. But the randomness is sort of more precise in a certain way. It has fewer choices to be made in the definition of it. And we can actually demonstrate something. And so the idea again is that kind of the gold standard of randomness is we have some Haar random object, Haar random unitary, or Haar random state. This is a very, very random object. It's not like the system will be exactly Haar random at any fixed amount of time, unless it's very long, but it can approximate to some extent a Haar random object. And that approximation is going to get better and better as you evolve for longer and longer time. That's going to be the idea. And so as I said, we're going to really try to think about, we want to have some number k moments of a unitary or state. And we want to ask, to what extent is that collection of objects the same as you would get, or statistically indistinguishable from what you would get for a Haar random thing versus some more structured object. So just really emphasize there's a change in focus here. Previously, we were talking about this one growing wormhole. Now we're going to be talking about a whole ensemble of growing wormholes. These will be our caterpillars. And we're going to say something about the properties of the ensemble, not about the properties of any single one of them, at least not directly. It's really the ensemble that we can characterize most easily. And it's this ensemble which is going to become sort of more and more random as the length of the wormhole gets long. So let me tell you now, this technically what is we're going to try to calculate. What is the diagnostic? And I'm going to use something called the frame potential. So this is a way of basically diagnosing whether or not a given ensemble has the same kth moments as the Haar ensemble. So the way you do it is as follows. You take two independent draws, U and V, from your ensemble, curly E. You compute this trace. You raise it to the 2k power, and then you average over your samples. Okay? And you can show pretty easily that if the ensemble E is Haar, this is equal to k factorial, at least as long as k is not too large. And moreover, if you have some other ensemble for which this is close to k factorial, then you know it's close in a precise sense to Haar. In fact, the difference of these two things is the difference in 2 norm between some notion of something called moment superoperator which characterizes these moments. So if this is close to K factorial, then the ensemble is close to Haar in the sense of reproducing K moments. So let me tell you about what we had done a few years ago, which was the impetus for this. A few years ago, we were looking at just qubits, looking at a model called Brownian circuit model, actually originally due to Patrick and friends many years ago. The idea of this model is like, just look at this top line, you have some dynamics in which you couple a bunch of spins or qubits together with all possible 2-qubit interactions, and you have a bunch of coefficients here that are random in time. So every possible coupling has its own independent white noise random variable, and you're going to average over these different things or take different samples of them to have your ensemble of random. And what we did several years ago was say, okay, we can actually calculate spring potentials for this kind of circuit. And you can then compare it to this K factorial, ask, how close we need to be to have a really strong notion of a K design. And what we found is that the time you need to evolve this circuit for to reach a K design scales linearly with K. And that's kind of the best you can hope for. Technically, what we did is we mapped the calculation of this quantity for that Brownian circuit to an effective quantum statement. So there's an effective Hamiltonian, which I'm calling here HK. I just write it here for you if you want to know. It has a lot of structure. It's maybe hard to decipher at first glance, but it has a lot of structure. And this spring potential is just a thermal partition function of that Hamiltonian, where the time, little t, that you evolve for is playing the role of beta, the inverse temperature. So long time is like very low. And what you can see, if you study this Hamiltonian for a while, we can sort of know everything about this Hamiltonian actually, but if you study it for a while, you'll see that for k equals 1, there's one unique ground state, which is just bell pairs between the forward and backward top, right? And we know the whole spectrum of the Hamiltonian, we computed analytics. There's a finite gap above the ground state. We know how many states there are, and we're good. When you increase k away from 1, then you find now there's k factorial ground states. You pair the forward and backward, the u's and u daggers together, and there's k factorial ways of pairing k copies of forward and k copies of backwards. And then again, we know the spectrum. We know the gap analytically. We can compute the low-lying spectrum approximately, and we can actually calculate based on that what the spring potential is. We find an expression like this. So then if you just ask how long does t need to be, how large, so if this is very close to 0, sufficiently close to 0, then you get that conclusion that I said on the other side. Now, just for later use, I just want to mention that we can also present the same problem as a path integral. Instead of just analyzing the Hamiltonian directly, we can recast the partition function as a path integral calculation. I put it in gray here, so there's a formula, but don't worry about the details. And if we evaluate that path integral by saddle points, using large N as a control parameter, we get again some answer, and that answer just exactly matches the answer we got from the direct analysis of HK. And the picture again, you have the dilute gas of excitations at long time, which correspond to low temperature. And then if you plug in that answer into some precise bounds on some very strong notion of being K designs, the diamond distance, then you again have the conclusion that it approaches the K design after at most time proportional to K. Let me skip this. Just say like, so that was what we had done a few years ago. And the idea was, and we did that explicitly with this circuit growth, interior growth picture in mind, but that was for qubits. We wanted to really turn this into something about black holes where the geometry was really there and explicit. Okay. And so the idea was we want to do the same kind of thing. We want to take the Hamiltonian of the CFT, and we want to add a bunch of random sources to it. That would be like adding our Brownian noise. Here's the form of those sources. But the problem here is that this is going to cause heating. So it's it's not we have one black hole which we're messing around with. We have a whole bunch of black holes that are getting bigger and bigger and bigger, and they're expanding, and that makes it hard to talk about one particular energy window. They're black. So we need to do some cooling as well. That was the new ingredient. And the way we're going to do cooling is just to do imaginary time evolution. So we just, it's not even really unitary. We just damp the energy essentially. And this, when you do the gravity calculation, turns out to basically mean the sources are effectively placed inside. So you're not like throwing in energy from outside which falls in, you just directly put inside the black hole, and that's where the randomness lives. The randomness lives inside, and it's always kind of thermalized at all times from the outside. And so the precise state we're going to get is very reminiscent of the thermofield double state. You have energy eigenstates or some kind of basis on the left and the right. Energy eigenstates in this case would be unperturbed, the non-Brownian Hamiltonian. We have some thermal factors, and then we have this object U, which is sort of like our random unitary or random like matrix. And so it's really like this object that we're going to constrain the properties of. That's going to tell us about the frame. This is a technical thing to say exactly what we're doing. I won't want to dwell on this, but for technical reasons, we use what in the business are called time folds. So you have some real-time evolution with the perturbation, then you cancel part of it with the same backwards evolution without the perturbation, and then some Euclidean evolution. So you kind of do the randomness, cool, do the randomness, cool, do the randomness, cool. So you always stay in some energy window. And the important point here, I'm not going to explain how you calculate all this. This is too broad an audience for that. I'll give you a little bit of flavor later. But the important thing is that just like with the Brownian spins, we can present this calculation now, frame potential, as a path integral. This time it's a gravitational path integral, so it's sort of sum over geometries. And we're going to evaluate that path integral with the same approximation that worked well for the Brownian spins, the saddle point approximation. Now the role of large number of spins is played by large 1 over g. So remember all the way back at the start of the talk, the entropy of the black hole is proportional to 1 over g newton. So that very large entropy turns into a very strong control parameter that says as long as you have lots of degrees of freedom, this saddle point is a good approximation. And so that's the kind of limit we're working with, very classical.
In the system you're actually studying, there's no gravity, it's just like the qubits.
Yeah, that's right. Indeed. So there's like just the CFT point of view, which is what I wrote there. And then, as I said, we can separately say this is also a gravitational path integral using the ADS CFT dictionary. And that's what we're gonna use to relate this purely boundary notion. So everything I said here makes sense from the CFT point of view. There's no gravity at all.
Talking about really CFT, it's just a quantum circuit.
Just a quantum circuit. And so this is a little bit of an artistic, this is sort of artist commentary, a cartoon, because actually solving for the metric with a given particular set of sources is a little bit hard to do. But spiritually, at least, it should look like some sort of complexified geometry with lots of patches. Each of these patches are like these different random sources that we've turned on, some particular instance of them. And again, the length of the wormhole just corresponds to the time that you've evolved for. So now at last, the main result again, we have this ensemble of these caterpillar states, these wormholes with features inside them. They have some average length L, and there's something that sets the units, and then this set of wormholes will form a quantum state K design. So those states are just like random states in the energy window of the black hole, and they reproduce the kth moment of the full distribution to a very high precision if the wormholes have length L. Okay? So in other words, this is a quantity that you could calculate in your lab. If you're simulating this system, the CFT, with the random sources, you could in principle compute this by doing a whole bunch of experiments and averaging. And then at the end of the day, that number you got out, you would say, okay, it's a 10 design, not an 11 design. So I know that the wormholes have this length. And then we can also use the fact that we know that design relates to complexity in some way to say those states must also have a certain complexity, which must grow at least linearly with time. So we also kind of get that in a sense for free. The caveat is that we're talking about the ensemble, not a single particular state. So just a little bit about, this is, maybe just like more of a comment for the experts. I've mostly talked more generally, but how do we actually do this kind of calculation on the gravity side? So here's an example of the frame potential for k equals 1. I just have 2 copies of psi and 2 copies of phi, right? Which are 2 independent draws from my random state ensemble. I compute their inner product squared. And if you calculate the average of this, averaging over those Brownian couplings, you get another effective stat mech problem, just like with the Brownian spins, but now with a new ingredient. So here are your kind of random, this is like what you have for the Brownian case. Now you have new terms which correspond to the Hamiltonian of the CFTs. So it's kind of a combination of the Hamiltonian of the CFT plus this Brownian effect. And this Hamiltonian sort of coupled system between different copies, this has appeared before. It's called the Molosine G eternal wormhole Hamiltonian. Its ground state, which is what would control the effective stat mech problem at long time, is like the thermal field double. So that's like saying that at long time, on average, this state from one side or the other looks like a thermal state. That's what we want. On average, it looks like a black hole, a featureless black hole. And the gravity side, that thermal field double is just one of these simple wormholes here, without features. So that thermal field double kind of comes back again in a different guise now as a useful technical thing. And so these kind of wormholes are how we actually figure out on the gravity side what this frame potential is via the map between the path integral and the frame potential. Okay, I'll skip this. There's sort of a general argument you can make. If the operators have a certain property, then you expect gravitational solution of a certain type, which corresponds to these wormholes that I discussed before. But that's sort of technical. So the physics is really that these terms want, what's the ground state of this whole thing? Well, these terms want to minimize the energy from the CFT point of view. This term wants the 2 copies to be correlated, and the combination of those 2 things, the competition between them, gives you an entangled state, which is like a thermal field double, at a certain temperature, which is related to how J compares to this other system. So just a few comments. If you want to see completely explicit details, we did what everyone would do, which is take JP gravity, a particularly simple model of ADS CFT. And we worked out all the details of all these wormholes and all these solutions and all that stuff in JT. I already mentioned that the effective Hamiltonian you get has this form that was talked about by Molosine and G and many others. And this Hamiltonian is interesting in part because if you want to prepare thermal field double states in the lab, one strategy might be to make this Hamiltonian in your device and cool it down. That would be a way to make a thermal field double. And so actually that's another interesting connection. I mentioned like what we can access most easily are ensemble averages. It's sort of harder at least to say precise things about the individual caterpillars. They're sort of complicated. But it is interesting to look at fluctuations. You can calculate the fluctuations by looking at more complicated kind of wormholes. You can also get control of this in like simpler models. So this is the picture I opened the talk with. This is the simpler kind of caterpillar where the perturbations are strictly symmetric. So they're just uniform in space. Then what you have is just a wormhole that has the same spherical symmetry, but little dust shells corresponding to the perturbations you've thrown in. Like you have some matter that you perturb the system with. That matter in the bulk corresponds to just particles that are behind the horizon. So you have like dust shells of different energy, and you get this segmented geometry. You can do things like calculate what is the average length of this compared to the fluctuations in the length, and you can find that the length is a self-averaging quantity. So the length here is a Gaussian variable that would have relatively small variance in the usual way. And then, just again, this 3 factorial or k factorial, which is so important in getting a frame potential for higher k, that comes in this way of thinking. The dominant contribution is just you make pairs between forward and backwards. So it's like pairs of these multi-unity wormholes, these thermofield doubles. And the number of ways to pair is 3 factorial. So it's a kind of simple class of saddle points to the gravitational path integral, which we're claiming is the right ones to compute this frame potential. Okay. That's the Dutch shell model. So, okay, that's the story I want to tell you, more or less. What I hope you take away from this is that, the interior is in a sort of mysterious place still. I think that's a fair statement. I mean, we understand something about it, but nothing compared to, how we understand the outside. And there are these sort of complexity geometry conjectures that were very inspiring, but a little bit hard to pin down. And I think we've given a kind of precise version of those by changing the focus a little bit from one state to an ensemble of states, and by thinking about randomness instead of about complexity. They're related, but the randomness is sort of the more easily accessible note. And so you can, in principle, probe the interior as long as you have lots of copies of a state and you do some statistics, at least for this ensemble. And then maybe, a little bit more broadly, the tools that we think about in thinking about this problem actually have broader relevance. So I showed you the tensor networks and how they're actually useful for like more ordinary kinds of quantum simulation problems. Even though that integrable CFT that I showed you, the Ising chain, has nothing to do with gravity as far as we know, it's a totally different kind of system. Still, the technology seems to work there. And also from the point of view of these frame potentials in random states, random circuits, some of the technology is perhaps of interest if you just want to make, random circuits in the lab. So let me close them with kind of a dream. What's the dream here? The dream is that we could build one of these systems, one of these CFTs in the lab, right? And ask a question of it using our experimental apparatus that we couldn't answer any other way. Some hard question about quantum gravity. We would get an interesting answer out, hopefully. And then we would learn something very non-trivial that we would not have been able to calculate or know. Unfortunately, doing experiments that probe the quantum nature of gravity in our own universe are very challenging. They're probably far away. And so this might be one complementary and very powerful way of gaining insight into potential theories of quantum gravity. And so from this point of view, you can say, well, we finally have a precise observable. It's very onerous to calculate this in the lab, to measure it. You need to do lots of work. But if you did all that work, then you could, for this ensemble, figure out how big the interior is. So you actually have some precise way of diagnosing. And, actually, this is just a preview. I'm not going to say anything about this, but I think there's even better ways of learning about the interior, which use multiple copies of the state. So stay tuned for that. And just also advertise there's a whole interesting world of what kinds of models, what kinds of systems would realize this physics. And there's lots of room there to think about new kinds of models and how you might implement them in actual platforms. My most recent interesting model is what we call the sparse spin SYK model. It's a very sort of simple model of state. You just have a bunch of Pauli operators like X, Y, Z, sigma X, sigma Y, sigma Z. You consider, say, Q-body interactions of those things with some fixed but random couplings. And maybe you don't even need a lot of these. You can just use a small subset of all of those Pauli strings in your Hamiltonian. And we did some calculation that showed that as long as these operators are, say, 5-body or more, you would also have gravity coming out of this. But unlike fermions, which you have with normal SYK, this set of spins is probably a bit easier to access in the lab. Okay, so we're kind of getting closer and closer to like the minimal possible system you could have that would realize this physics and then try to do it That's the. And ultimately, can we learn about the nature of the singularity, or about closed universes, or about cosmology from a quantum simulation? That's kind of the long term hope of this program. Okay, thank you a lot.
I have both, I don't know if it's a question or a suggestion.
Okay, I'm happy to hear you.
Yeah. What is actually extracting the information about the
Yeah,
caterpillar from in the interior, pulling it out to
yeah,
seems to me the natural proof for that is some form of quantum. Anybody thought about that? And if not, it's a suggestion of something that will be.
yeah. I guess as usual, I've thought about thinking about it, but yeah, I think it's a great suggestion. Thank you, Douglas.
So in your main result, was this based on computing the frame potential using gravity?
Yes.
And then for the factor relating the frame potential to the diamond norm, you just put e to the s.
Yeah, that's a very good question. So for this, where did it go? Yeah, sorry for this grayed out thing. Yeah, here, we need to be a little careful about whether we're like truncating the tails, whether it's microcanonical or canonical. And so we discussed that at some length, but I think there's still some, I would be hesitant to make like a very precise theorem-y sounding statement about exactly what's happening. But yeah, roughly speaking, you would say you truncate the microcanonical window, and then you put in that dimension there, and we would say that you would be densely filling this window a very long time with these caterpillar states.
And is your impression that that is not just a bound, but it's correct, or like?
That's another excellent question, and I don't know. I have some. I mean, I think from the point of view of how fast it can form designs, it couldn't be any faster.
Well, the coefficient could be different.
But the coefficient could be different.
You have kind of a nice coefficient in your main result.
Yes. Yeah. So short answer is I don't know. I think it's a good question. I just don't know how to access that diamond norm like more directly. But that's also something that I thought about thinking about, but didn't think about too much yet. Yeah, Adam.
Cool. So yeah, it seems like one of the main ideas is that you're doing this cooling step where you're like projecting yourself back into the low energy state.
Yeah.
Can that be efficiently implemented but
well, I would say almost certainly no. So in that sense, what you need to do, like if you want to like literally do this, the most direct thing would be to like do post-selection, where you measure the energy, and as long as the energy goes down, you keep it. Okay, so it's possible, but it would be expensive. However, what I suspect, this is work in progress, if you go back to my aside, which wasn't completely besides the point, this is like a map from like low energy degrees of freedom to the UV. I can think of it as an isometry of sorts, which maps kind of the entropy degrees of freedom of my thermal state to the UV. So what I want to do is like literally think of putting a random circuit down here at that scale and running it, because this corresponds to the horizon where it's thermalized. That would correspond to putting them right at the horizon or just inside the horizon. And so I think you can actually make these caterpillars practically, as long as you have an efficient isometry, which embeds the entropy sort of thermal degrees of freedom into the UV. And I believe that these Mera circuits can do that, but we have not like demonstrated that conclusively yet.
I asked this like my co-authors and I, something like Tamara, for example, this group, we're asking questions recently in our last paper about like, can you make low energy forms of quantum pseudo-randomness?
Yeah.
So,
I think it's
if you could make something efficient, it would be extremely super.
yeah, I think that's a great question. Yeah, in the back.
Yeah, so I have maybe a more basic question. In general relativity, the coordinates don't mean anything. So taking a time slice is kind of an arbitrary thing, but in the CFT or these qubits, it's clearly time is meaningful. And then you showed a number of slices where states in the CFT corresponded to a certain time slice going through the ER black hole.
Yeah.
How are you choosing time slices?
Yeah, great question. Yeah, so this, as you say, there's lots of notions, like, so this boundary point is like well-defined, but then there's lots of space-like surfaces that connect these 2 points. And there's been a whole literature about like how to choose those surfaces, like what's the right one to measure the complexity and so forth. One idea was that this should be a maximum volume slice, which connects these 2 things. So that's a diffeomorphism invariant definition of some surface, not designated coordinates. Another idea that we worked on was maybe you take the entire like causal, like Lear-DeWitt patch, the whole like set of all of these things, maybe that should be associated with the complexity somehow. So there's like tons of ideas of precisely how to quantify this. But yeah, there are sort of variant notions of what these slices should correspond to.
Okay, and then my next question was on a later slide when you were putting the black hole into the matrix product state for the qubits on the surface. You replaced the sites that would have gone into the black hole with thermal states, but all of the cuts that you showed earlier should go through the black hole onto the other side. They shouldn't be cuts through, like they should be wormholes, it seems like. Did you,
Wormholes.
like if you go back to 2 slides, when you're drawing this space-like surface, it goes all the way through black hole one side or the other. But then you do this calculation where you're looking at qubits on the surface of this tensor state.
Yeah.
And then when you insert the black hole and you calculate its entropy based on going around the rim, you're saying like you replace all of the things that would have entered the black hole with thermal states.
Yeah, so I mean, so that would be like this picture where there's only like there's nothing inside, it's just lines that connect like this. You just join up the lines. But more generally, this is like a flat geometry. And so we know minimal curves in flat geometry are straight lines. So basically either it can go like this or it can go like that. And so that's why it kind of sits along the horizon. Because here it's kind of curved, but then once it reaches the horizon, it becomes flat, it flattens out. And so the curve just hangs there because it doesn't pay to dip into the flat space region at all. You just have a straight line there. So that basically think of it as coming down, it hits this region, and it doesn't pay to go inside, so it just flies along that surface and then comes back up.
Great, thank you.
Yeah. Yeah.
General question. So from the, if I think in the Brandeis theory, then the interior dynamics like determine because it's not changing. But if I think from the boundary point of view, the interior, what happened in the interior region, like in the future, what happened in the exterior. So naively, that's not determined. It's like I have my exterior dynamics where my boundary is known, and then in the interior, I could put in different things, like maybe different possibilities as well.
Yeah.
So the question is whether in general, there is a reason that the interior dynamics is determined by the boundary.
Right.
Like naively, I could have a cubic going in, and then I just suddenly change my mind and I don't want to get to it.
Yeah. Indeed. I mean, in general, I would agree. Like from this, where's the picture? From this point of view, like I've shown up like a random circuit while I'm here, and when I'm at this stage, I only see part of that random circuit that's in here. So I still have freedom based on what I do up here, or depending on how it's thermalized yet, like some region of time, I still have freedom to decide like what's going to happen in this part of the geometry. So in principle, there is some freedom from this point of view. Now, the fact that I'm using these Euclidean parts, I think complicates that idea of causality a little bit. So I'm not precisely sure what to say there. But yeah, I take your point.
Hi, Brian. I saw in your last page you said that this kind of tensor network stuff can be apply to the cosmology of the city-states? Can you say more about
I definitely did not say that.
that? Oh,
Did I say that?
I saw there is some lines in your last page. Or-
I mean, that is what people have done or thought about doing, but what did I say? Okay, let's look. Let's discover together what I wrote.
I just saw the word cosmology.
Okay, yeah, yes. But it's not directly to do with the tensor network. It's more about multiple copies of the state. The essence is that you want to do a modular evolution with a given state, but you don't necessarily know what the state is. Like it's like think of it as a black box. Then you can do the modular evolution using a quantum circuit as long as you have many copies of the state. So modular evolution lets you kind of look inside in some way, and you can simulate this modular evolution by using lots of copies of the quantum state. There's a standard trick for doing this.
Yeah, but why is modular evolution the right thing to do if you're not in fact familiar with it?
Well, that's a more complicated story, which, yeah, it would take me like a while to explain. And I actually don't, I haven't written the paper yet, so I can't say I'm 100% sure. But yeah, that's the idea.
Okay, I think maybe in the interest of time, we should wrap up and Brian.
Thank you.